Thank you. So hey everyone, I'm Jake Massimo, and I'll be talking about joint work with Martin Olbrach, Kenny Patterson, and Yuri Soromovsky, which is Prime and Prejudice, Primality testing under adversarial conditions. Okay, so give an overview of our work and what we'll be talking about today. First, in this work, we analyze the implementation landscape of primality testing in cryptographic libraries and mathematical software. We review and extend existing techniques to produce composite numbers that have the best chance of fooling these primality tests. And for each library, we test them against adversarial input and relate this to the performance that these libraries give in documentation. Okay, so first we're going to start with a little bit of motivation and background, talking about why prime numbers are important within cryptography, and then we'll move on to some fundamentals of primality testing and how we might produce composite numbers that fool primality tests. Then we'll move on to some contributions and results before ending with some conclusions and recommendations. So first, motivation and background. Why are prime numbers important within cryptography? Well, of course, many cryptographic primitives rely on hardness assumptions that are based on prime numbers. For example, RSA, finite field Diffie-Hellman. Now, even if these primitives aren't explicitly dependent on prime numbers, perhaps they might use prime parameters to prevent some attacks, such as the divide and conquer approach, as seen in the Baillie-Hellman algorithm and in Limley small subgroup attacks. Finally, primality testing can be pretty useful for us. The generation of prime numbers in devices is usually done by just sampling numbers of the desired bit size and randomly and repeatedly primality testing them until we're happy that this number is indeed prime. Okay, so how do we know that a number is prime? So there are two flavors of primality testing. We have deterministic primality tests and probabilistic primality tests. So deterministic primality tests can prove conclusively that a number is prime, but most of these algorithms are still too slow to be practical in most cryptographic scenarios. So instead, we often use probabilistic tests, which is the main focus of today. These can only prove that a number is composite, and it does this by using an arithmetic condition that we know that holds for all primes and repeatedly apply this to the number that we're testing. If we find a contradiction, then we know that this number is composite, but if after, say, t rounds we haven't found such a contradiction, then we just say that this number is probably prime. Okay, so within cryptography, the environment in which we're testing is very important and will be a theme throughout this talk. So there are two main types of environment, and the first is, are we testing on a random input? So is this number that we're testing random? If it is, then we can apply theoretical bounds that are given to produce average case error estimates. So these say we take the bit size of a number and we know how many rounds of testing we need to perform, and we'll have some sort of probability or an error estimate that this an error estimate that it is not the case. So for example, an error that this number isn't prime when we actually think it is. So in the example I gave earlier, just again to reiterate, when we generate primes, we know for a given bit size how many rounds of testing we need to perform. Now the other case is the adversarial input case. So this will be when we are maybe not generating the numbers ourselves, but we're taking them from someone else. And in this case, we need to treat them perhaps as if they aren't random, they may be hiding some malicious intent. So here we must consider the worst case error estimates, which can often vastly differ from the average case. So for example, if prime generation is too expensive on our particular device, we may instead opt to have the primes given to us from another source, in which case we have to validate and verify that these numbers really are prime. So a good example here is within public key parameters. So throughout our talk, the libraries we see in the wild mostly are only considering this random input, and we want to test to see how they really fare against the adversarial setting. So I want to give some concrete examples of this adversarial setting and how adversarial inputs can be used. So some recent examples from Valenta et al. And Fried et al. 2017, who study RFC 5114, which promoted some Diffie-Hellman subgroups that were shown to be partially vulnerable to small subgroup attacks. Another example is from the command line data transfer utility SOCAT, which published a security advisory that stated that their hard code 1024-bit Diffie-Hellman prime parameter P was in fact not prime. Okay, and lastly, another scenario that we can keep in mind is within instant messaging apps that promise end-to-end encryption. Now, sometimes the cryptographic parameters are supplied by the server, so therefore, for the clients to have end-to-end encryption, they need to verify that these parameters really are honest and do the job that they say they should. Okay, so now some fundamentals of primality testing and how we can generate composites that can be declared prime. So the main focus of our talk today will be on the Miller-Rabin test, as it is a highly popular probabilistic primality test that we see used in all libraries in the wild. So this test is based on the arithmetic condition that we know that holds for all primes, which is the non-trivial square root of unity. So here we take a number n that we want to test and a base a, and this a is not a multiple of n, and then we have these two conditions that we can test. Now, if both of these conditions do not hold, then we know that n is declared composite, and we denote this a that we use to test as a witness. If either of these two conditions hold, then we say that n is probably prime, and we call that a non-witness. So this can be quite a lot to take in, and so to give an intuition of what's really going on, there's a nice example we can draw with a lottery. So here we have n lottery balls, where n is the number that we are testing, and the bases a are the individual lottery balls themselves. Now we remove the edge cases 1 and a equals n itself. So here we look at here we have one round of Miller-Rabin is equivalent to drawing one lottery ball, and the balls can be either of two colours. So if the ball is red, this indicates that A was a non-witness and tells us that n is prime. And if the ball was blue, then this indicates that this A was a witness and indicates that n was composite. So if we're testing a prime number like 47, the distributions of balls would look something like this, right? All red balls, so no matter which balls we chose for Miller-Rabin, it would indicate this number as prime. A composite number, however, would look something a little more like this. We'd have a mix of both blue and red balls. So here we're testing n equals 50. And if we were to do 7 rounds of testing, i.e. 7 rounds of Miller-Rabin, our draw might look something like this on the right. Now, if we have at least one blue ball, then we say that this n is composite. And in this case, we correctly declared so. If our draw looks something like this, we happen to get unlucky and picked all red balls, then we would incorrectly classify this number as prime. So this is the sort of scenario that we're looking to find. So one of the most important parts of your Miller-Rabin implementation is how you pick these bases or how you draw these balls. And this can be done in one of two ways. So the first way is fixed, right? So this Miller-Rabin test will always choose the same bases for testing. So this might just be the first t prime. So in this example, we do the first 7 primes. Similarly, we could just make a random selection from a fixed list. So these two things can be thought as essentially the same thing. So then the work of Arnaud describes a method in which we can generate adversarial composites that always have non-witnesses to a given set of bases. So here we just make sure there's a red ball in every one of these bases. So every time we test this number, it's going to be declared incorrectly prime. The other way we can choose bases is by doing it randomly, which, provided that the source of randomness is good, means we shouldn't be able to predict which ball is going to be picked. Then the best we can do is, we know by the Miller-Rabin bound that there can be at most phi of n over 4 non-witnesses, where phi is a Euler phi function. And this basically means that 1 in 4 balls are red, right? About a quarter of the balls. So Monnier described a method in which we can generate composite numbers that have this maximum bound of non-witnesses. And since it's roughly a quarter, so for t rounds of testing, we have a 1 in 4 to the power of t rounds probability of fooling the test. Okay, so a random draw might look something like this. We hit a blue ball here, so we would correctly classify this number as composite. It might look something like this. We hit a few reds, but it didn't matter. We hit a blue, so again, composite. This time, we got pretty unlucky, or maybe lucky, and we hit all red balls and incorrectly classify this number as prime. Okay, so to give an actual distribution of some non-witnesses for some small examples, we think of what a developer might have in their head when they're thinking about calling a Miller-Rabin test on a random input. So this is the distribution for n equals 700, and you can see there's essentially a sea of blue balls with just a couple of red dotted throughout. So here we might just do a couple rounds of Miller-Rabin testing, say 2 rounds, and we're extremely likely to pick a blue ball. Therefore, we have a good hope that we correctly get this right. Now, in an adversarial input, this is the actual distribution for 703, which has 160 non-witnesses, or roughly a quarter. So if we were to treat this as if it was a random input, we might still be doing just a couple rounds of testing, but in this case, we're much more likely to pick a red ball both times. Okay, so now on to our contributions and our results. So thinking back to the bigger picture, we have all these methods of generating adversarial inputs, and we have all these primality tests in the wild that are mainly set up for random numbers. So how can we join the two together? So first, one of the things that we had to do was scale these existing techniques and set them up for using cryptographic size numbers. The next thing we also had to do was tweak these generation methods to make sure they were both efficient and would beat the bespoke testing that each library would do. And we'll see a little bit more detail about that in a few slides. We also managed to create a hybrid of both methods, which you can kind of see illustrated by this diagram here, which will give us non-witnesses to a fixed set of bases, but will also have the maximum number of non-witnesses. So this might be useful for some particular tests we see in the wild. So here, just to give a brief overview of our results, we summarize them in a table of which we classify how the rounds of Miller-Rabin was declared. Was it chosen by the user, or perhaps was it set based on the bit size of the number? We then give the documented failure rate. So in documentation, what the library says, or how often the library says this test should fail or give an incorrect result. And we also look against the actual failure rate when given adversarial input. So if we look at the top example of OpenSSL, we can see that the number of rounds of Miller-Rabin used by default is based on the bit size of the number. They give a failure rate of less than 2 to the negative 80. But in fact, when given adversarial input, we can get composite numbers declared prime with probability 1 in 16. So we'll have a little closer look at what's going on in OpenSSL, as well as look at GNU GMP, libtommath, libtomcrypt, and wolfSSL. So OpenSSL, for those who don't already know, is the most widely used open source cryptographic library and TLS implementation. It's the default encryption engine for Apache and Nginx web servers, which host a massive 62% of websites online today. Now, the Primality test, as we said before, performs random-based Miller-Rabin, where the default number of rounds is based on the bit size of the number. So we'll have a little closer look at exactly how this works with a little snippet from the code from OpenSSL. So here is the function that takes as input B, the bit size of the number, and returns how many rounds of Miller-Rabin that you need to perform. And they give, in the documentation just above there, this is an error rate of less than 2 to the negative 80. So for a number that's 1,300 bits or more, this is just 2 rounds of Miller-Rabin. So, of course, we know that we can construct composite numbers that have 2 or 3 factors that have this maximum bound of non-witnesses, or red balls. Therefore, for a 2048-bit number, we know we're doing just 2 rounds of testing, and therefore we can have composite numbers declared prime with probability 1 in 16. Now, if you're a developer that's using OpenSSL and you want to use their Primality test, you might think to yourself, okay, how many rounds of testing do I need to use? I've got no idea. Let's see what OpenSSL says. Oh, cool. They give this function that can tell us how many rounds based on the bit size, and the error probability is tiny, right? 2 to the negative 80. I'm done. I'll use that. That's fine. But if this developer isn't carefully thinking about where this Primality test is used, then it might be on adversarial input, in which case they're going to be given much higher or much more likely to have incorrect classifications than they originally thought. So we don't even have to look far to find a use case, an incorrect use case of this. So within OpenSSL's own library, they have the Diffie-Hellman parameter checking function, DHCheck, which takes a Diffie-Hellman public key parameter set and tests it for validity. Now, one of the tests it does is check that the parameters are prime, but it uses the default method of basing the rounds of Miller-Rabin on the bit size of the number. Now, of course, if we're receiving a Diffie-Hellman parameter set from someone else, we can't be sure that these numbers are truly random or non-malicious. So we should be considering this adversarial case. Okay, next we look at GNU GMP, which is a popular open source arbitrary precision integer library, which is widely deployed in mathematical software packages and cryptographic applications. So the Primality test in GNU GMP first performs some trial division. It then performs a single Fermat test, which is sort of like a basic Miller-Rabin test that uses Fermat's little theorem. It then does T rounds of Miller-Rabin, where the user must pick T. So GMP in their documentation gives some guidance of how many rounds of Miller-Rabin, and they give between 15 and 50. Now, what's interesting in GMP is how these bases are chosen. Now, they're chosen via a pseudo-random number generator, which is seeded with an identical state each time the Primality test is called, as we can see in this little code snippet on the side here. And therefore, the sequence of bases that are used are chosen for Miller-Rabin when testing a particular value of n is fixed with respect to that n. This means that if we're able to generate a composite number that is declared prime by T rounds of testing, it will do so every single time it is called with GMP's test. So Using sieving speedups inspired by the literature, we managed to construct a 1024-bit composite number that is declared prime for the minimum recommended rounds of testing, which is 15. Now, this number has the form n equals 2x plus 1, 4x plus 1, with x of this specifically crafted form to make use of this sieving and also to beat this little Fermat test that they're doing just before. So although this was quite costly to generate, we had to do trial 2 to the 47 candidates, which took just under 4 core years of computation. We managed to find it, and here it is at the bottom. And we'd like to thank Cloudflare for kindly donating the server time. Okay, lastly, we'll wrap up by looking at wolfSSL. And now wolfSSL is a small TLS library that's used in embedded systems. And here the documentation gives an error probability with at most 1 over 4 to the power of t for t trials. So you can see they're sort of thinking these worst case scenarios, these adversarial inputs. So the primality test here is actually calling on libtom-math and libtom-crypt to do their primality testing. They share the same code base, so we can actually look at all 3 libraries at once. Cool, so here the rounds, again, so the testing is done by T rounds of Miller-Rabin, where T is user-defined and must be less than 256. What's interesting here is wolfSSL actually stripped the user's choice of T and hard-code it to the value of 8. So here the bases are chosen as the first T primes. So we know, using methods inspired by Arnaud, that we can just simply generate composite numbers that have red balls or non-witnesses in these first T prime positions. And therefore we can produce 1024-bit composite numbers that are guaranteed to be classified as prime for up to T equals 40 rounds. In fact, we can go one step further and scale this method up to all 256 primes. So whatever valid choice of T the user chooses, we're guaranteed, that the test will declare this composite number as prime. One small caveat here is that this number actually blows up pretty big, and it's around 7,000 bits. Okay, so just to end things with some conclusions and recommendations. So for software developers, we recommend that they consider carefully this distinction between primality testing on adversarial input and random input, and think about this in their cryptographic implementations and in their respective documentation. We want them to think about how their primality test is used, either elsewhere in the library, as we saw within OpenSSL, or by the end user themselves. We can ask them to consider the limitations of probabilistic primality testing and the benefits of implementing the Baillie-PSW test, another probabilistic test, which is a Miller-Rabin, and another test for which there are no known pseudoprimes. Also, if they want to keep their code base down, then perhaps just to implement Miller-Rabin with a pseudo-random selection of bases. We also ask that they consider the use of standardized parameters wherever possible in the public key cryptography. Now, for cryptographers, we ask you to think about how developers interpret your work. Maybe you have these elegant formulas for the average case estimates and the worst case estimates, but to a developer that just wants to know how many rounds of Miller-Rabin they're doing, they might not be sure on the distinction between these two and the restrictions that this has on their implementation. And even there's a lesson for mathematicians. We ask that we consider studying the Baillie-PSW test and look for composite numbers that can pass it. So thank you for listening. Are there any questions?
There's a question over there.
Hi. Have you looked at standards and what they recommend, and is it to blame? Are standards to blame for any of this?
Yeah, so we had a look at what the standards are saying, and most of the standards that we come across are pretty switched on, and some of them actually do distinguish between this adversarial and random case. But I think that these messages perhaps don't get all the way through to the developer. So they are hidden away there in some standards, but it's not always. I don't think it's always clear to the particular developer of the library that how important and how bad things can really get.
Thank you.
So my question is, why, if the worst case is the proportion of bases that you need to pick scales with the number over 4, why is it that OpenSSL actually does fewer tests for large numbers?
Yeah, absolutely. That's a great question. It seems counterintuitive at first, right? So the numbers are getting bigger. Why am I doing less testing? So we can think about an intuitive way to think about this is that there will just be like a small handful of red balls or non-witnesses for any given number, right? We know as we saw in this previous example, we can think about something like this. So when the numbers are relatively small, maybe these balls occur 1 in 2 to the 40. And so when the numbers are small, then there might be a handful and we're more likely to pick a red ball with just a couple rounds of testing. But when the numbers get a lot bigger, say bigger than 1,300 bits, there might be a red ball every 1 in 2 to the 40. So we're very unlikely to pick a red ball at this case. So just 2 rounds of testing should be enough on a random input to have an error probability less than 2 to the negative 80.
Do you know of, was the number that they picked there informed by any particular?
Yeah, exactly. So they give their reference as the Handbook of Applied Cryptography. They even put it in this little blurb here, right? So these are like, it's based on this paper by Damgard et al. So they do like rigorous, like of the numbers this size in bits, then this is how many rounds of testing you need to do. And they use these formulas that I showed at the end to calculate that, essentially.
Thanks.
Cheers.
So for the number you've shown where you're able to fool the primality test, you've chosen it of a specific form with the as a function of
this one here, right?
Variable x. Yeah, can you say a little bit more about the reason why you chose it this specific?
Yeah, absolutely. So part of the inspiration comes from so the literature described, but also we saw in the recent Return of the Coppersmith attack papers on these RSA keys on these smart cards, right? And one of the things that they were doing was this efficient prime generation. And to efficiently generate primes, you use numbers of this form, this x equals k, which is like a buffer to get it to the correct bit size. And then we do a product of small primes pi, and then plus a number. So we know that this x isn't divisible by any of the small primes pi. So we're sort of constructing it with some sieving in mind, or some, And so then when we plug this x into our n here, we know that these primes here, these 2x plus 1, 4x plus 1, aren't going to be divisible by any of these small primes in P. So when we get a number out of it, it's much more likely to be prime than just a random choice, essentially.
So I assume there will be more details on that part in the paper.
Absolutely, yeah. We extensively talk about this in the paper, and there's a bit in the appendix as well where we go into a lot of detail exactly how we came to this and the methods used.
Thanks.
Thank you.
Okay, last quick question over there.
So pardon me. So the suggestion is to use the pseudo-random basis. What's the performance impact? Like how much more time does this take, and how bad is it?
Yeah, that's a good question. I guess it depends on your particular scenario, right? If a good source of pseudo-randomness isn't available to you, then this could be a tricky thing to do, absolutely. The other option of the Baillie-PSW test, there is some sort of benchmarks in literature that says it's roughly equivalent to just 2 or 3 rounds of Miller-Rabin. And for this, you don't need a source of randomness. You just do Miller-Rabin with a fixed base of 2, and then you do another test, a Lucas test, which may be more expensive. So perhaps if you're worried about a not good source of randomness, then maybe you might want to look at this other source of testing.
Thank you.
All right. Thank you very much.